So welcome everybody to this webinar of a series dealing about our benchtop instruments to perform flow chemistry. So I'm Matthew, an application chemist at ThalesNano, and I will hold this webinar. So today we are going to talk about a scaling up option, the H-Genie plus Phoenix platform. So let's go through the plan of this presentation. So I will have a brief introduction before talking to you about the instruments, first separately and then in combination to form the H-Genie Phoenix Flow platform. I will explain to you the scaling up reactions before showing you directly under the fume hood the setup I've created. And it will be then the time to answer your question. Okay, so this is already the 5th webinar. So I'm not going to develop flow chemistry into this one, since the previous one are dealing quite well with it. But I will put a link into the video description for you to see it if you want more information. So a few words about ThalesNano first. So we are making laboratory reactors that chemists can use to create new drugs, new aromas, new chemicals, or even new processes. And you can see here some important figures and a picture of the HQ Pro. We've already talked in the second webinar. So let's have a quick look at our portfolio. So we have a wide range of instruments for different kind of chemistry. So for example, for really exothermic reaction, we have the ice cube. Now on the other side of the spectrum, we have the Phoenix and the flash pyrolysis platform. Now if you aim at working with gases, with hydrogen, we have the HQ Pro family. We already talked about in the previous webinar, and we have this combination, this platform, the H-Genie and Phoenix. Besides those, there's also the photocube that is for the photochemistry. So let's see the H-Genie first. So it can be used on its own as a standalone hydrogenator, as well as in combination with another reactor, whatever it is, batch or flow. So the flow rate can be up to 1,000 normal milliliter per minute. It can deliver hydrogen pressure up to 100 bars with a purity of 99.99% minimum. So I remind you, like, the hydrogen is made by the electrolysis of water. And this figure actually can be even increased up to 6 nines if you use a dry cart system directly inside the water tank. So it is also fume hood friendly, I would say, since it is compact enough to fit it under a fume hood. And you can use it easily for a dozen of hours without refilling it, as it has a water reservoir of 3 liters. Eventually, you can also control it and capture the data directly with a computer, or you can simply export the data with a USB pen drive. So here are the main advantages of using such an instrument. So first, and without doubts, the most important feature is safety. The hydrogen being produced in real time, on demand, the volume stored is actually very low. So it's less than 150 milliliter, which is a big advantage over cylinders. So no risk of explosion, neither fire. So also you can monitor the hydrogen consumption directly on the display, on the screen. It can build up hydrogen pressure up to 100 bar, as I already said, but it enables like difficult reaction, making them quicker. So you can also easily fill up multiple reactors in parallel, since hydrogen production can be as high as 1 liter per minute. And you can also do batch and flow chemistry. The accuracy of the flow rate of hydrogen is 1 milliliter per minute, which allows you to dose equivalents of H2 very accurately for screening, for example, for optimization studies. And it is also very simple to use. Within minutes, you can have set it up and ready for a reaction. And of course, it has inbuilt safety features. So you can see here on this picture a different application, what it can be used with. So it can be used, like, for example, for filling balloons that you can use later on for your batch reaction flask. You can also fill pressurized reactors, autoclaves, or even shaker reactors. But today, we are going to connect it to flow reactor, and especially the Phoenix flow reactor. So the pressure and range of this reactor is really broad. You can perform reaction from room temperature up to 450 degrees and up to 200 bars. You can decide also between heterogeneous reaction and homogeneous. I will come back to it in the very next slide. It is also safe. A heat exchanger is connected when the temperature is high. There's emergency stop in case of communication error, and a connection to nitrogen gas is feasible for more efficient cooling. You can either use it on its own, like just as a heating reactor, or with the H2 Pro, and you can control it from the H2 Pro, so directly on the interface of the H2 Pro. So that will increase capabilities in terms of temperature of the H2 Pro. And you can also combine it with the Genie, which is the subject of today, to increase the capabilities in terms of the hydrogen flow rate available. And the reactor zones are also customizable. So about the reactor zones. So there's two kinds. The one for heterogeneous chemistry, when you have a catalyst in a solid phase, for example, and the one for homogeneous chemistry. For homogeneous, you have coiled reactor. It is a stainless steel tube, usually, because it fits most of the application, but you can find different materials as well. And you have different sizes according to the residence time you are aiming at. Basically, you have 4, 8, and 16 milliliters, but you can also have some tailor-made sizes. For heterogeneous reaction, it is in a form of cartridges. So either a CAD card for the small scale, MIDI card for, I would say, average scale, and metal sealed column for scaling up. it has a longer residence time then, and it bears a higher temperature as well. So to give you an idea, it can go up to 80 milliliter, the internal volume of the column. So you can see here on this picture one of the simplest setup of the Phoenix on its own. So you have on the right the pump, the HPLC pump, and then the reactor, the Phoenix reactor itself, and then the back pressure module at the end. Now it is time to talk about combining those two instruments into a new platform. So what are the main benefits of doing this? So it has a high throughput that is time saving and increased productivity, of course. Also, the reaction conditions are high, up to 450 degrees and 100 bars. You can easily achieve productivity of a small production manufacturing site, I mean up to few kilograms. You can centralize the control it from further away from a computer. The handling is pretty easy, and within few minutes you can just have it operational, ready for your reaction. And the safety is guaranteed at large scale. So now just a quick reminder of the main advantage of flow chemistry over batch chemistry in terms of safety. For the same quantity produced, flow chemistry is much safer. You can have here a grasp of the different hazards related to batch reaction. For example, you have the hazards related to the nature of hydrogen that can provoke fire and explosion, related to the catalyst handlings, which can be pyrophoric in some cases, the hazard related to the use of solvent, which can be flammable and then increase the risk of fire, and also the generation of the intermediates, which can be quite unstable and provoke explosion. And this is even more concerning as you are scaling up, since the volumes involved are more important. So scaling up multiplies the risk in batch mode, and so we divide them or avoid them in flow mode. Now, we have also another scaling option, and in this comparison table, you can see the main difference. So, the main benefits are the throughput of both liquid and gases, and also the temperature that allows you to explore part of the spectrum not achievable before. So you can see the liquid flow rate and the hydrogen flow rate is higher with this platform. But more than just giving you those specification and compare both instruments in terms of specification, let's create an example. And let's take this hypothetical reaction. So it's a pneumatic ring saturation. I choose it on purpose because it's a high demanding reaction in hydrogen. So 3 equivalent are needed to reduce the full aromatic ring. So let's set the same conditions to make the synthesis comparable in both cases. So molar concentration of 0.2, 3.3 equivalent just to be sure and to have a slight excess. Now the max size of the reactor for the Phoenix being about 60 times the volume of the MIDI card. That means we have to fill it with 10 times more the catalyst, with the catalyst. And then the flow rate will have to be 10 times more to keep the same residence time inside the reactor, inside the cartridge. It also means that the hydrogen consumption would be 10 times higher to keep the same equivalency. And then you could achieve easily 10 times the productivity if you are making sure, of course, to keep the catalyst activity over time. So while you would achieve 184 grams a day with the H-Cube MIDI, you would achieve almost 2 kilograms a day with the HGenie Phoenix platform. Those calculations are based on a hypothetical yield of 90%. So now I did it on purpose to select not the most optimized conditions, so a yield of 90%, high demanding hydrogen reaction, so 3 equivalent, with not the best optimized condition, neither the worst, but somewhere in the middle, more realistic and closer to the kind of synthesis I guess you would encounter. And even in those conditions, you can achieve way more than 1 kilogram a day. So my point is to show you that even with a high equivalencies reaction in H2, you can reach the kilogram scale. And you can also note there's room for higher productivity since the equivalency could be optimized, I mean lowered. The molar concentration could be increased as well. And if there's some room left for optimization, you could also increase the flow rate with a higher throughput pump, of course. So now I want to show you a work we have started, but we are still ongoing. So we will publish the application note about it in the next couple of weeks. So this is a reaction, a Nitro Reduction already performed on the H-Cube MIDI. And we are now performing it on the H-Genie Phoenix platform. So far, screening runs have been performed in order to see the conditions that can be optimized or changed. Also, a first run of few hours has been done to synthesize about 30 grams of product over 3.5 hours with a simple MIDI card. A longer run will be done in the very next step, and if the conversion and yield are stable over time, we can expect a productivity minimum 10 times higher, like in the previous example I showed you. And in parallel, further investigation can even increase the productivity, like the molar concentration and the equivalency of hydrogen. So now it is time for me to show you the setup in the laboratory environment. So I am now in front of the setup. So you can see here there's 4 instruments / modules. So I'm going to detail each of them by following the flow of the gas and the liquid. So it will give you, I hope, a better picture about what is the pathway of your reactants and product through the system. So, but first, let's talk about the H-Genie. So the H-Genie actually is produced by our sister company, ThalesNano Energy, and it won an award in 2019 to the RID Top 100. So this H-Genie produce the hydrogen for our system. And so I'm going to describe you the screen. So you can have like different options according to the application you need. You have also the status bar here, which indicates you the current status of the instrument. Right now, it is in standby. That means it is ready and waiting for your next comment. You have the water level sensor here, and you have like few other tabs to get info and follow the parameters through a graphic. So first, let's go to the different application. So different options depending on what you want to do with your hydrogen feed. So for example, you can fill in balloon if you wish to use it like to connect it to a flask vessel then. So you have to select the volume of the balloon in hydrogen, the volume in hydrogen you'd like to. Okay, you have also the option for a batch. So if you want to link it to a batch reactor, so you can see there's like different parameters now. So you have to select the pressure of the vessel and the filling rate in hydrogen of your vessel. But right now, we are interested in the flow because it is like in the flow system. So let's click flow and describe it a bit more. So you have two even different parameters. So you have the reaction pressure and the hydrogen flow rate. So to modify those, you have little buttons, but the best way is to go to the keypad and just enter your value and click OK. And then let's do the same for the flow rate. So let's put 250 normal milliliter per minute of hydrogen. Okay. Now I've set my values. You can see here, just as an information, you have two set of values. So the one you set and the actual value. The actual value you can see, which is 0 right now because I didn't start the system. So then the status is in standby. It's waiting for my instruction. And so I'm going to start now. And as you can see, the status has changed. Now it's preparing the hydrogen pressure internally. So you can see, so it starts increasing. So it's going to take few minutes to build in the hydrogen. So while it's building this pressure, I'm going to show you the rest of the system. So first, so when the hydrogen is injected, it's coming out from this line. So then it passes first by this check valve. Check valve that is really necessary to prevent any liquid to flow back to my instrument and potentially damage the system. So the check valve, and then it continues until this union T here. But you can also have a gas liquid mixer. So this is at this part that my liquid will be mixed with my hydrogen flow. So you can see here, so my liquid line is coming, it's aspirating through the pump here, and so going to this mixer. So after the mixing happens, so it continues, and it goes to my reactor, to my Phoenix reactor now. You can see here, so it's open, so I didn't set the temperature right now, but it is to show you the inside. So you can see here, inside the heating chamber here, you have like you have holders. In those holders, you will put your cartridges. So this is the holder for the MIDI card, because right now in my system, I've connected the MIDI card with, you can see here. So it's ready. Placing it again. But you have to know, depending on your cartridges, like the size, the length, the volume, the diameter, you have different holders. So I will show you. I guess you show, if you followed the previous webinar, you saw some of them, but so those are like some other diameter column you can put so inside it, but with different holders as well. I will show you. So you can see here. So you have the column, and so with the holders. And so you put those holders, you replace those holders by the good one according to the column you have here. Oh, yeah, I almost forgot to mention, you can do homogeneous chemistry. So if you are doing homogeneous, you have a loop, you have this system, so you place the system directly in place of the holders inside. So now it is time to close our heater. Okay, and close the door. Okay, these two parts in the heating chamber. So to control of the temperature, you can control separately. One for the upper part, one for the lower part. If you have like big columns that use all the size, you would use like both control to have a uniform heating through all your column. But right now I'm going to put only the upper part, since my MIDI card right now is in the upper part. So to change the temperature, it's really easy. Oh, you have to see like these two different figures here: the temperature that is actual and the temperature that you will set here in green. So you just have to go through the little button to increase or decrease according to your needs. So you can see you can go up to 450 degrees of temperature, but in our case, let's set it to 70 degrees, and now it's set up. So within seconds, it's going to start increasing the temperature, and you can see it's starting now. So then what happened to my flow? So before I had my liquid line and hydrogen that passed through my cartridge inside my heater. So the reaction happened here, and so now I should get my product that will come out in this line. This line, which is connected here to a back pressure module. So this pressure module is made of pressure sensor, the back pressure regulator here, and a valve that can be easily used to switch between, for example, your waste solution and your product. So as you can have now a global view of all the system. I'd like to show you some more options and some more functionality on the H-Genie. So let's go back to it. As you can see now, the status has changed to stable. That means now it's delivering, it's providing the hydrogen. And since 2 minutes, almost 3 minutes, as you can see the time here. So, I'd like to show you also that is very easy to change the flow rate, even while it's working. So you don't need to wait again that the hydrogen is building up as at the beginning, but you can just do it by clicking stop and then just going to this keypad and like changing it. So let's changing it to this value, and then I press start again, and within a second it's stable again because the hydrogen was already inside, so it's ready now. So I would also like to show you like the two other tabs here, so to get more information. So in the info tab, you have different values. You can check on the gas flow rate. So this is the gas flow rate we set and the gas flow rate that is delivered then. The output pressure of hydrogen that is coming from here. Maybe you could have heard this sound. So that is the sound of the hydrogen that was coming out of the line. So I don't know if the micro was enough for you to hear the sound, but now the hydrogen is coming out from the line with my liquid. So okay, let's go back to the screen of the Genie. And so you have like, different information. You can also check the feed volume of hydrogen, the water conductivity, the water temperature. So all kind of information. You can also go and in this question mark here, if you click on it, you have different other tabs that can help you to set up your Genie or to change some language. There's 5 languages right now. There's also like how to use the interface tutorial and so on, different information. Some troubleshooting help also. And there's another tab which is important as well if you'd like to monitor your hydrogen feed. And so this is the graph tab. And you can visualize the pressure inside the cell, the pressure of the hydrogen delivered, the flow rate in orange here, and the volume. So all those information can be monitored as well from a computer, or it can be simply exported through a USB pen drive. So now I think I explained all the basic you need to know about this platform, so the Genie Phoenix platform. So it is time with my colleague Norbert to answer your question. Yeah, perfect. So now it's time for your question. So feel free to send your question via the chat on YouTube. So anyway, if you have any questions afterwards, you could still ask them like with to the address askthechemist at ThalesNano.com. So I will wait a couple of minutes to see if any of you have any questions. No question. So meanwhile, I'm taking the opportunity to tell you we don't know yet about our next webinar, but it's going to be probably after the summer. So, but we will let you know as soon as we know. Oh, so some question just arrived. So what is the minimum gas flow rate? So for the H-Genie, I guess, for the hydrogen flow rate, so the minimum is 100 milliliter per minute. The maximum is 1 liter per minute. But you have to know you can also decrease less than 100 milliliter per minute, but the accuracy wouldn't be as good. So that's why we decide to put a minimum of 100 milliliter per minute. Can you control the flow of H2? Of course. So it has like a 1 milliliter per minute accuracy. So which makes it quite convenient if you'd like to screen the different quantity of hydrogen you would like to inject in your line. So reactor volume. So it depends. You have like actually quite a broad range of reactors volume. But so with the Phoenix, you can use every reactors from the cat cart, like the 30 milliliter cat cart, which has a volume of like 100 of microliters, up to the big metal sealed column, which are until up to 81 milliliter. So you can see you have quite a broad range of different volumes depending on your needs, actually. And it is the same for the loop. Like, I mean, if you are looking to do homogeneous chemistry, so you have different size of loops. Like, basically, the most common are like from 4 milliliters to 16 milliliter for the loop. And so the catalyst capacity, so I guess you mean the quantity of catalyst you can put inside. So to give you an idea, so in a MIDI card, which is the intermediate size, which is the one actually we use for this demo. In the MIDI card, it has a volume, internal volume of about 6 milliliter, which allows you to put about between 3 and 4 grams of catalyst. But of course, it depends on your catalyst. But for example, if you are using palladium and carbon, 10%, you can put 3.5 grams of this catalyst into a 6 milliliter MIDI card. So next, which is the next? Oh, yeah, catalyst is used as pellets or as a powder. So far I've only seen with powders. I mean, it depends on the grain size of the pellets. Okay, I will check this information furthermore to confirm this, but I think it's more convenient for powder because of the size of the reactors, of the cartridges. So, yeah, are metal catalyst particles suspended? So the catalyst actually, except if it's a rainy catalyst, which will you have to store it and to put it under water. All the catalysts come like dry. So when you use it for the first time, it is not like in any suspension solution. So it will become as soon as you will start your reaction and to start on your flow. Let me know if it was exactly what you meant in your questions. So no other question yet. Okay. Anyway, yeah, I want to add so all of your questions. So I will answer them. I will write a more complete answer, and we will send it to you by mail in a couple of days in the next week, I guess. And any questions that will come up later, eventually, that we wouldn't have time to answer, for example, in this webinar. So, next question. What I meant was so the particles of the catalyst are so they are kept, they remain inside the cart, like because it is closed by both ends by different membranes. So yes, it is remaining in the reactors, like as long as you don't open your reactor, so it stays. If we use corrosive gases, it's a packed bed type. Yes, of course. If we use corrosive gases, it's possible to. Yes, of course, of course. Basically, you have three choices, but which can also be customized. But first, it comes with stainless steel material, but you could also use PTFE. Of course, you have to know with PTFE the temperature limit is not the same, but you can also use alloy material, of course, if you are working with more corrosive material. It's totally possible. Next, how do you scale it up to 1000 liter per hour if you use packed bed type for catalyst? I mean, okay, I don't know if I understand the question correctly. But actually, I mean, if you want to scale up, you would, of course, use bigger reactors. So the biggest we have right now is a 1-inch column, which you can put like 80 milliliter, 80 milliliter internal volume, which allows you to put about 50 grams of catalyst. So because you would have a very big internal volume, you could increase the flow rate as well, depending on the residence time of your reaction, of course. But then you could reach quite good flow rate. Any other question concerning the gas liquid mixer? So what I used here, it was a simple union T. It was not a proper gas liquid mixer. So this is like simpler. It's just a 3-way connection. But of course, as I already mentioned in the presentation, you can of course use a gas liquid mixer, which is more efficient in some cases. So I can send it afterwards more information about this, since I don't have like all the technical detail right now, but I will send it to you the answer. Okay, if there's no more question right now, so I wanted to add. So feel free to ask any other question if you are watching the video afterwards. To send us the question directly at askthechemist@thalesnano.com. So we will answer them, of course. Oh, another question just popped in. What does the mixing within the reactor? I don't really get the question. Could you please rephrase it? How does the mixing within the reactor? Thanks a lot. You're welcome. Okay. Gas needs to be mixed with liquid. So in the column, so there's like the mix of the 3 phases, so the hydrogen, the gas, the liquid, and the catalyst, the packed bed catalyst. So you have your three phases in the reactor. Okay, so yeah, I will let you know as soon as I know the next webinar, probably after the summer. And don't hesitate to tell us if you would like, if you have any particular need for the next webinar, or you would like to know more about a particular instruments. So thank you very much for your attendance, and yeah, I'm looking forward to see you in the next webinar. Thank you very much. Yes, and I almost forgot to say the webinar will be available on the website, ThalesNano.com. Thank you. Goodbye.